Eva, can you hear me?
Yes, madam.
Okay, morning. We was unable to continue our class due to the power fail. So I start again the evening session. In the morning session, I already uploaded recordings to your knowledge, right? You can follow it. Now I am continue from uh, uh, photoelectric effect. We discuss about the photoelectric effect and some results, right? Mm, I think you remember. Can you see the screen? Can you see the screen?
Yes, madam.
Yes, madam.
Yes, right. Okay. Then we discuss photoelectric features and the results and the classical predictions. I think you remember. Then later I will explain the reasons for this one, right? And explanations, right? Then we discuss about this equation, photoelectric effect, work function, and things. You can see one equation here. Electrons ejected from the surface of the metal and not making collisions, then with the other metals, atoms before escaping possess the maximum kinetic energy kx max. In your books, it is mentioned as ek max, no problem. And we can write k max equal hf minus psi. Psi naught is the correct one. The correct one which we can take the psi naught is called as the work function, right? And the useful notations. We can write this equation in your page number 21, 2.2 is the equation. You can see 2.2 and 2.3. K maximum, kinetic energy maximum. Here, EK max is equal HF, H nu. Also, we can take H nu. Nu is the frequency minus phi naught. Phi naught is the work function of the metal, right? The work function represents the minimum energy with which an electron is bound in the metal, right? Then we will see other parts. Then next we can discuss some questions. Here, then equation. This equation is K maximum. Ek maximum. Kinetic energy is equal HF minus psi. Then this is the some graphs, right? The lines shows the linear relationship between K max versus F. F is the x-axis. Frequency is the f-axis and kinetic energy maximum we are taking to the y-axis. So, in this equation, K max equal HF minus psi, you can see the relationship of this equation is related to the y equal mx minus c. Right? Can you understand? If we are taking K max into the y-axis and frequency in the x-axis, this is same as y equal mx minus c, right? So you can see this graph, then metal 1 metal, and you can see then intercept. Intercept equal minus phi naught. Phi naught is the work function. Then if we want to find the work function related with the photoelectric effect graph, we can take the intercept of the line, right? Then metal 1, metal 2 and metal 3. And also you can see these all lines are parallel. Why? Why all lines are parallel? Anyone can answer the metal 1, metal 2 and metal 3. These are the linear graphs and you can see the angle between x-axis and the graph, if not gradient. Gradient of the graph, gradient of the graph are equal and lines are parallel to each other. What is the difference? What is the same idea? Anyone can give the idea about this? The graph is equal K max equal HF minus psi. It is related to the y equal mx minus c, right? Why these different lines are parallel to each other? Hmm? Why? See this equation and you can answer. Hmm? Anyone can answer? You have to read the
Planck
graphs.
constant.
Planck constant. Yes, then you can see this graph is K maximum equal HF minus psi. The graph is Kmax versus F, and H is here. H is the gradient of the graph. H is Planck constant. It is the constant. So for the middle, for difference middle, intercepts is equal to Planck constant. Very good, right? The lines between this linear relationship you can see, and the slope of each line is 8. The x-intercept is, we call this as the cutoff frequency. What is the cutoff frequency? Here, in the x-axis, the maximum kinetic energy goes to 0. At that point is cutoff frequency, right? Intercept of the x-axis, we can find the cutoff frequency for the metal 1, metal 2, and metal 3 like this. And also you can find work functions, the phi 1, phi 2, and phi 3 intercept of the graph, intercept of the y-axis, right? If they are giving some graphs, you have to answer this question. What is the cutoff frequency? What is the Planck constant? And what is the work function of the graph? Then you have to read the graphs, right? Okay. Then photons with energy, then there we can find the cutoff frequency. This frequency below which no photoelectrons are emitted. The cutoff frequency, right? Then cutoff frequency and wavelength. The cutoff frequency is related to the work function through Fc equal phi h naught. Why we can say phi or h naught? At the cutoff frequency, what happened? You can see in this figure. This is the frequency below which no photoelectrons are emitted. Then after the below the cutoff frequency, we cannot see the emitted of the photoelectrons, right? And you can see here what happened at the cutoff frequency, maximum kinetic energy goes to 0. Right? Then the equation, this equation Kx is equal 0, then equation become HF equal 5 naught. And you can find F value according to this equation. Fc, cutoff frequency is equal 5 naught over H. 5 naught over H. The cutoff frequency corresponding to the cutoff wavelength. Then lambda c is, we can find C over Hc, Hc over phi naught. The wavelengths greater than lambda c, incident of material having a work function psi, do not result in the emission of photoelectrons, because then at the below of the cutoff frequency, no photoelectrons are emitted. This means then wavelength greater than lambda c, cutoff wavelength greater than lambda c, no any emissions of photoelectrons. I think you can understand, because frequency below value and lambda c greater value, because 1 over fc is proportional to lambda c. If lambda c increasing, fc is decreasing. So the below this value, we cannot see the photoelectrons emissions in the Fc, but greater than lambda c, we cannot see photoelectrons same, right? Then we can call this as the cutoff wavelength. You should have thorough knowledge about what is the cutoff frequency, what is the work function, right? Okay. Then after getting some questions, I want to explain again this results, right? Please understand and practice this. Okay. Then in the results, experimental observations, we compare. Previously, we compare with the classical predictions, right? So we can explain this one. We can describe this. Uh, these are the results. These are the experimental results. We can explain this by photon theory of light or photoelectric effect, and we can describe this with why these arguments do not work in classical. Right? Previously, I explained about the experimental. Same thing here. The first thing is No electrons are emitted if the wavelength of the incident light is increased above some cutoff wavelength lambda. Then we can explain it. This is the one result. No electrons are emitted if the wavelength of the incident light is increased above some cutoff wavelength lambda. This is lambda t, cutoff wavelength. This is the one experimental result. But in the classical prediction, they say any intensity is increasing can emit electrons. But this is different with the classical theory, right? Here, I will explain it. In the next slide, you can see it. Please follow up these things, right? Then we can explain this. According to the Einstein photoelectric equation, uh, you can see here EK. I think better to use the board, right? Then after explaining this. Okay. We are asking about what is the statement is no electrons are emitted if the wavelength of the incident light is increased above some cutoff wavelength lambda. One of the experimental results. We can explain it into the quantum mechanics and we can describe why classical arguments do not work in it, right? In the equation, photoelectric effect equation, we can write EK maximum or EK, kinetic energy. Maximum value if you are taking, it's equal to the work function and other things. EK is equal H mu minus phi. Phi is the work function, right? Then we can rewrite this equation. So I am writing this. Uh, this is called this as the cutoff frequency. They mention as the cutoff frequency. Then we can write this as H nu is equal H nu t cutoff frequency plus E k. Chi also the wave function. Then we can rewrite this equation as H nu equal H nu t. Here the cutoff frequency plus Ek. Ek is the kinetic energy. And also we can write here H c over lambda is equal H c over lambda t plus E k. And also this one equal 5 plus E k. So we can describe by quantum theory. Psi is the work function, or we can take this as W, the work function. Ek is the maximum kinetic energy of the photoelectric, and lambda t is the threshold frequency or cutoff wavelength of the threshold wavelength or cutoff wavelength, right? The electron can only absorb one photon. I described this previously. One photon according to the quantum physics. If Hc over lambda less than Hc over lambda t, the electrons would not have enough energy to escape the surface because we need this equation. The lambda t is the threshold value, it is greater value. So this part is, this part is limited value, then this part is higher than this one because this is smallest value, right? Then we can see electrons would not have enough energy to escape the surface since its energy is below the work function. Then, so the prediction, experimental results is okay. no electrons are emitted in the wavelength of the incident light is increased above some cutoff wavelength. If this is increased value, this one, it is smaller value. This is the cutoff value. So lambda is increasing, what happened? This part is decreasing. So which can compare it with cutoff wavelength, this one is less value than this one. So this is the photon energy. Then this is not much enough to escape the surface, escape the electrons from surface, right? Below the work function, since its energy is below the work function. In the classical theory, electron can absorb wave-like light slowly and eventually escape once it has enough energy. Also, according to the classical theory, the process of transfer of energy to the electron should be independent of wavelength but depend on the intensity. In the previous slides, we explained it, right? So we can compare this. It's the lambda t is cutoff wavelength. Increase in the wavelength. Increase in wavelength means Hc over lambda is less than this value. So the less value, no enough energy to escape electrons, right? So, but in the classical theory, we can move to the slide share. Then you can see here what is the explanation we need for this one. First one, no electrons are emitted if the wavelength of the incident light is increased above the sub cutoff wavelength lambda t. The explanation given here, you can see, right? Everything here, the threshold wavelength. So electron would not have enough energy to escape the surface since its energy is below the work function. However, in classical theory, electron can absorb. In classical, it's okay. Wavelength slowly and eventually escape once it has enough energy. Also, in the classical theory, the process of transfer of energy to the electron should be independent of wavelength or frequency and depend on intensity. Right? It is various in quantum theory. Right? We can explain next one, next experimental results. Previously, I also discussed with you. Here, I want to summarize that, right? If the light intensity is increased, the maximum kinetic energy of the photoelectric remains same. This is the one other experimental results, right?
Excuse me.
Then, how we explain it? You can see same equation I am taking here. Hc over lambda. Can you see the screen? Right?
Yes, madam.
Madam, we can
Okay.
see.
Okay. Nituna is there, no? Hc over lambda is equal Hc lambda 1 plus Ek. The rearrange the equation. W plus Ek equal h nu. The energy of photons are equal h nu, which are independent of intensity, but it is proportional to the frequency of light which has photons. However, according to the classical theory, light in wave form will have greater energy and greater intensity. That is, associate energy depend on the intensity. We consider light consists of photons, then we could get greater energy only if we increase the frequency, right? Then this is the next experimental results. I think you remember. I summarize all the things. This is the one, classical prediction and experimental. Then experimental one, here I am explaining according to the quantum theory, right? You have to read more and more and try to understand, right? I will share this PowerPoint also, right? In OULMS. Right? Then second one, intensity increase, the maximum kinetic energy photon in the remains same. And I explained here, this is. The energy photons are equal h nu, which are independent of intensity, but it is proportional to the frequency. We know it, right? Of light which has photons. Then in the classical mechanics, classical theory, light in wave form will have great energy at great intensity, right? But it is independent of intensity in quantum theory. The third one, the maximum. These are the experimental results in photoelectric effect. Now we are explaining according to the quantum theory and failure in the classical theory. The maximum kinetic energy E of the photoelectrons decreases with increasing wavelength of the incident light. It is also you can explain, right? We know third one, right? V equals C over lambda. This is equation and E equal H nu. HFO HC over lambda. Lambda increase means whatever frequency decreases, right? Then H nu frequency decreases. Then whatever energy of the photon, this equation is related to the photon, the incident light wave, right? The energy of the photons will decrease because nu decreases. The energy absorbed by the electron will decreases. That is, the maximum kinetic energy photoelectron will decreases. And fourth one, electrons are emitted. I also explained this previously from the surface almost instantaneously. Then time is less than 1090 seconds, independent of the light intensity. In the fourth one, in the classically, electron absorb wave-like light gradually before escaping. Thus, T very much greater than 0. But according to the quantum theory, the electron absorbs photon and gains energy instantly. But in the classically, it is more time. But here, quantum mechanically, electron absorbs photons and gains energy instantly. Right? I think you more practice and practice because sometimes a question will come asking about the explanation of the photoelectric experimental results. One or two can come, right? Then I explain two times, feature 1, feature 2, 3 and 4 and also here I summarize all the results, how failure with the classical theory and how treat with the quantum theory, right? Then you have to practice it, right? Before going to the quantum effect, we have to discuss some questions, right? Waiting room නම් දැම්මේ නැහැ. කවුද මේ? ඇයි?
मैडम ළමයි වගේකට ලොක් වෙලා
Waiting room දැම්මේ නැහැ.
ගෲප් එකේ මැසේජ් දාලා තියෙනවා කියලා.
නිපුණ ඔයා නිපුණ නිපුණ ෂෙයා කරාදරක මම ඊමේල් කරා ඔයාලට කොහොමද ලින්ක් එක ගත්තේ? OULMS එකෙන් විදුල
මම ෂෙයා කරා මම.
ඔව් ඊමේල් එකක් දැම්මා ලර්න් OS එක දැම්මා මම නිපුණට දුන්න ගෲප්ස් වලට දාන්න.
ईमेल
ගෲප් එකට දාන්න කවුරු හරි.
ඔව් මම දෙන්නම්. ඔව්.
ඒකනේ.
मैडम
ලොග් වෙන්න බැරි ප්‍රශ්නයක් නැහැ. ඉතින් ඔයාලා ලොග් වුණේ නේ.
मैडम මම
ඔව්
ලින්ක් එක
නිපුණ
ගෲප් එකට ෂෙයා කරා. ඒ ලින්ක් එකෙන් තමයි මම හිතන්නේ ළමයි දෙතුන් දෙනෙක්ට මේ ලොග් වෙන්න බැරි කතාවක් ගුගේ දාලා තිබ්බා. මේ ලින්ක් එකේ ගැටලුවක් නෙමෙයි මම හිතන්නේ මේ සමහරට කවරේජ් එකේ හරි මොකක් හරි
ඔයාලගේ ඉෂුව
ප්‍රශ්නයක්
එකක් වෙන්නේ නැති නේ.
ඔව් ඒක තමයි. දැන් අපිට ගැටලුවක් වුණ නැහැ. मैडम मैडम
මම ඊමේල් උත් කරානේ ලින්ක් එක.
मैडम
හැමෝටම ඊමේල් කරා. ඊමේල් එකටත් දැම්මනේ බලන්න. අපි කරගෙන යන්න.
ඔව් මම ඊමේල් එකවල තියෙනවා.
Yes. Correct. We will discuss some question related to the photoelectric effect, right? Okay, I think you have to write down, right? Electrons are ejected from a metallic surface.
Ma'am, excuse me. Madam.
Yes. Can you see?
යා मैडम दे මෙයාලා මෙසේජ් කරලා තියෙනවා waiting room එකේ ඉන්නවා කියලා.
මේකෙන් ලුම් දැම්මේ නෑනේ.
ඔව් मैडम මෙසේජ් දාලා තියෙනවා මට.
කවුරුත් waiting room නෑ. මොකද මම waiting room disable කරා.
waiting room එකෙන්
නෑ waiting room ඉන්න බෑ. එයාලා පෙරමින් තියෙන්නේ.
දන්නේ නැහැ මම.
मैडम मैं लॉग වෙන බැරි මැසේජ් කරලා තියෙනවා. ලොග් වෙන බැරි කට්ටිය waiting room එකට යනවා.
waiting room දාලා නෑ දරුවෝ. waiting room disable. මම waiting room අයින් කළා දාන්නේ link එක. waiting room ඉන්නවා නම් මෙතන පෙන්නන්න. එයාලා උදේ link එකෙන් ගියාද දන්නේ නෑ නේද? උදේ link එක update.
මම group එකට දාලා තියෙනවා. ඒ link එකෙන් තමයි මට message කරලා තියෙන්නේ.
ඔයාලා ගියෙත් ඒකෙන් නේද?
ඔව්.
waiting room දැම්මේ නෑ. මේකේ නෑ. try කරන්න කියන්නකො තව සැරයක් කියලා. Electron sum, please write down this question. Can you see the screen?
Yes madam.
Electrons are ejected from a metallic surface with a speed ranging up to 4.6 into 10⁵ ms minus 1. When light with a wavelength of 625 nanometer is used. Right? They are giving lambda value. And electrons are ejected from the metallic surface. It is speeding to 4.610⁵ ms minus 1. The first question is, what is the work function of the metallic surface? Second one, what is the cutoff frequency? For this metallic surface. Okay, two parts here. Then read. Electrons are ejected from the metallic surface with speed ranging up to 4.610⁵ ms minus 1 when light with the wavelength is given. Right? Then this is the related to the photoelectric effect because electrons are ejected. Right? Now you can write the photoelectric effect equation. We have to familiar with, right? Then you have to remember equations, right? What is the equation? We can write. Shall I read this one? What is the work function of the metallic surface? Phi naught is asking question is phi naught. Phi naught is asking, right? Another one, cutoff frequency. Then we can answer is omega. It is the nu t or ft is asking. Then we can write phi naught equal h nu minus ek. Ek is equal h nu minus phi naught. Then we can rearrange the equation. Phi naught equal h nu minus. What is this one? Kinetic energy, maximum kinetic. H is the Planck constant and nu is the frequency, photons frequency, right? Okay. Then we can write have to find phi naught and given wavelength. Given value of wavelength is 625. Then this is can rearrange as C over lambda minus Ek. Then how we find the equilibrium? Others are okay. H is the Planck constant for the calculation given. These values are given. Planck constant, velocity of light, the lambda is the data, and Ek is the kinetic energy. How we find the Ek value? How we find the Ek? Kinetic energy? Vidula? V maximum is given. Maximum speed is given, right? So, electrons, the particle, then we can find Ek is equal half m e v maximum square. V maximum square, right? Okay. Then me is the mass of the electron. Also, they are given data. Ek equal half 9.11 10 minus 31 and 4.6 into 10 5 square value. Then you can find Ek value. Hc over lambda 625 into 10 9. 10 minus 9, right? Please convert all the units to the standard value. Okay. 10 5 into 625 into 10 minus 9. Then you can calculate phi naught value. Okay. Then next one, what is the cutoff frequency? What is the cutoff frequency? When cutoff frequency, I think you remember the graph. When cutoff frequency, what happened? Kinetic energy. This is the related graph. Here, in one metal, this is the cutoff frequency and Ek. When the cutoff frequency, kinetic energy goes to 0. Then equation is, we can rearrange phi naught equal h nu. Because at the cutoff frequency, Ek is goes to 0. This is nu lambda, nu t. Right? Then we can find nu t value phi naught over h. In the previous calculation, we found phi naught value and h is the Planck constant. Then you can calculate nu t value. Okay? Can you hear me?
Yes, madam.
Yes, madam.
Okay. Then this is the one question. Now we will look the another questions, right? Regarding the photoelectric effect. Right. We have to define some definitions. I will describe it, okay? In the photoelectric effect, we have some terms, but photoelectric work function, stopping potential, and threshold frequency. Threshold frequency or cutoff frequency. Then we can define these terms, right? Photoelectric work function. Work function, what is psi naught or psi? Right? Then we can define what is minimum energy required by a photoelectron escape from a metal by overcoming the Coulomb potential. Because then we want to escape electrons, need to overcome Coulomb potential, Coulomb force, right? So this is the minimum energy need to required by a photoelectron to escape from the metal surface by overcoming the Coulomb potential we call photoelectric work function. Next one, stopping potential. We explained this in the previous slides, but I want to summarize, right? Stopping potential. Stopping potential. Why? The electron current reaches zero. The potential exceed V naught. At that point, EK maximum equal E T naught. The stopping potential. Other one is threshold frequency. In T. Cutoff frequency. Other word is cutoff frequency. And the minimum frequency of the incident radiation. Incident radiation. Then what happened at the result frequency? Kinetic energy is zero, no? It is zero, right? Okay. Then these are the threshold frequency. Right. Shall we move to the question? This question is related some Planck constant and also photoelectric effect, right? We will see. This is easy one. The uniform monochromatic beam of light of wavelength 4000 angstrom falls on a cesium plate. Cesium plate having a work function of 2 electron volts. 2 electron volts. The beam's intensity. The beam has intensity of 3 into 10⁹ what? N minus 2. This is combination of Planck constant and the photoelectric effect, right? Question number 1, part 1. Calculate the corresponding energy of the (4,000 angstrom) photon in electron volt. How we calculate this one? Photon wavelength, the uniform monochromatic beam of light means consists of photons. Wavelength is 4,000. Question 1. Calculate the corresponding energy of the 4,000 photon in electron volts. In the morning, we discussed this type of question. What equation we can use? Can you remember Planck's hypothesis? How we find the energy of the photon? Vidula? Also in the relativity part, I discussed the energy equation, mechanics of energy mechanics. How we find the energy of the photon? What is the equation? E equal Hc over lambda. Hc over lambda, right? C over lambda is corresponding to the frequency. E equal Hc over lambda. Then you can calculate energy of the photon. H is the Planck constant. It's the given value. In C is 3.10A and lambda 4,000 angstrom into 10 minus 10 meter. Then you can find E value. It's equal 3.11 electron volts, right? You can calculate it, right? The next one, the next question, number 2. Please write down this, right? Number 2. Considering the wave-particle duality, calculate the momentum. Calculate the momentum of photon with the above energy. What's the equation related to the momentum of the photon? Can you remember? Consider the wave-particle duality. Calculate the momentum of photon with the above energy. We know the energy. P
equal EOC.
P equal E over C. Yes, energy is given. And also we can use another equation. What is lambda equal H over P? Is also correct. No? Momentum can calculate easily H over lambda. H is the Planck constant, lambda is 4,000 angstrom, right? Okay. Then third one, third question asking, calculate the number of emitted photoelectrons in the unit time per unit area. Same questions we discussed in the morning, no? Calculate the number of emitted photoelectrons number of emitted photoelectrons in a unit time per unit area. Given intensity. Intensity is given. Wm minus 2 joule second per unit area. Right? The number of photoelectrons we can find. We know the energy of the electrons. We found it, no? Yes, in the first part, we calculate energy. Then ask in question, number of photoelectrons. 3.109 is given, intensity. We have to multiply 3.11 electron volts into 1.6 into 10 minus 90. Then we can find N is equal 3.109 minus 9 Wm minus 2. This means joule per second and square per area, right? Then we can divide this by energy of one photon, 3.11. We can multiply this by 1.61019 joule. Then you can find how many electrons emitted photoelectrons in the unit time. Okay, 6.03 is 10 9 m square s minus 1 per second, m minus 2 per unit time, unit area. These three parts are related with to the Planck idea. The next one, the question is here, right? It is including some Planck constant idea. Then now the question related with the photoelectric effect. Then find the maximum and minimum values of kinetic energy of the emitted photoelectrons. Fourth one, find the maximum and minimum kinetic energy of the emitted photoelectrons. Right? How we find this? In the minimum kinetic energy, it is equal 0. K minimum is equal 0. For the K maximum can find using the photoelectric equation. H nu, Hc over lambda. I can convert as Hc over lambda because lambda is given minus phi naught or phi. This is the cesium plate. Cesium plate. Work function is given 2 electron volts. So you have to convert this electron volts, so this one to joule. Right? Please think about units. Then K maximum can find Hc over lambda. H is Planck constant and C 4.97. The multiplication I can write 10 minus 19 joule over, we have to convert this is to 1.6 into 10 minus 19 joule electron volts, can convert to electron volts, and phi naught is equal to So you can find K maximum value. 1.11 electron volts. Right? Please check the answers. Then this is the minimum and maximum kinetic energy of the emitted electrons. Then other part, plot the variation of maximum kinetic energy. Variation of maximum kinetic energy, Kmax, of emitted electrons when the frequency f of incident photons are changed. Of incident photons are changed. Mark the threshold frequency and mark the threshold or cutoff frequency. In other question, I will write last question also. Above light beam falls on a silver plate. With a work function of 4 electron volt. Plot the variation of Kmax with F on the same graph and name them. Right? This is described about the cesium plate and it is work function is 2 electron volts. Now given one silver plate, work function is 4. Then we have to plot the graph. First one for the cesium plate, second one in the silver plate in the same graph and name what is the silver and what is the cesium. Then in the equation, I explained before, Ek maximum equal Hc over lambda or Hf minus 5. This is the work function, frequency and maximum kinetic energy. So, y-axis is maximum kinetic energy, x-axis is frequency. This is related to mx minus c. Now we can plot the variation. According to the cesium plate, phi is equal to 2. Right? And threshold frequency, at the threshold frequency, we know Ek is equals to 0. At the threshold frequency, maximum kinetic energy should be 0. So we can draw the graph. Frequency and Ek. In the cesium plate, phi value is with the minus intercept, it is equal to 2 minus 2. Then we can draw line. This is the minus 2. Work function and can mark, if not here, if not is the threshold frequency, this is the cesium plate. The next one, then what happened, we know gradient is same, it is equal to Planck constant, so it should be parallel with this one, but intercept is 4 because work function is 4, right? This is the work function for the silver plate. These two are parallel because gradient is represent the Planck constant H, right? Sometimes they can give one graph and ask in some question, what is the threshold frequency, what is the frequency and something, and given to draw another graph, right? And sometimes can ask to find the Planck constant using the graph, right? In the calculations, we are giving a Planck constant, but you cannot write this value. Then you have to use the graph to find the value for the Planck constant, right? I think everything can come. Every questions can come related to the photoelectric I explained, right? Now, and what are the features of the experimental results and how they are related with the classical mechanics and also classical theory and the quantum theory. I explained that. So we can move to the other session. Quantum effect. Quantum effect. Quantum effect, right? Are the holy quantum. American physicists then detected the lab at the University of Chicago. They discovered the quantum effect and got the Nobel Prize in 1927. Mm. Right. In your book, session number 3, can questions come? You can see here. Then all things are going to dual nature. These are the examples for dual nature of the EM theory radiations. Dual nature means particle-like nature and wave-like nature. In this phenomena, in the quantum effect, we can see also particle-like nature of the radiations, right? Particle-like nature of the radiations we can see. Right? Then two groups are doing this experiment. In the classical theory, it was failed to explain the scattering of X-rays. Right? In the applications, one applications of the quantum scattering can write in the experiment in radiobiology. We are using in gamma rays and X-rays for the study of the living organism. This one application of the quantum effect is, right? Material science, in technology, we use the X-ray diffraction something. Then these are also related to the quantum effect, right? In page number, right. In the photoelectric effect, a single electron absorbs the entire energy of the incident photon. These are the difference between the quantum effect and the photoelectric effect. In the quantum effect, you can see the incident photon only transfer the portion of its energy to one electron, right? In the photoelectric, a single electron absorbs the entire energy of incident photons. But quantum effect, the incident photon only transfer the portion of its energy to one electron. Then you can see the explanations. Right. This is the diagram related to the quantum effect observations. In experiment, you can see page number 28 and explanation of the equation, quantum shift equation in page number 30 and 31. Right? This diagram is related to the quantum experiment. This is showed that at any given angle, only one frequency of radiation is observed. Then F naught and lambda naught is the incident wavelength. Incident wave. And Then just like the collisions, the electrons and the one photon, right? Photons of energy h nu, hf naught, hf naught, h over lambda naught of energy. Then collection of photons. These are the waves treated with incoming X-ray, right? Incoming X-ray. Then we can say collection of photons, one ray with energy h nu. And this is the one electron, stable electron. Then collisions between the photon and the free electrons. Photon means, the particle of zero rest mass. Photon has the rest mass is zero. Then we can define the photon as the particle of zero rest mass. And it is collide with a free electron. Here, free electron, one free electron. To that, just like the billiard balls. And then what happened? Individual photons considered as scattering elastically, right? Then incident photon transfer to energy to electrons during the collisions. Then F dash lambda dash is the scatter photon. Is F dash lambda. The angle between the x-axis and the scattering direction is theta, right? The scattering photons is frequency is f dash and also wavelength is lambda dash. Then photon transfer energy to the electrons during the collisions. The recoiled photon which make up the scatter beam with the small energy than the incident photon E naught. Then E dash is less energy than the E naught. Then you can see recoiled electrons here with the electron recoils just as it is struck by a classical particle. Then angle of the scattering angle is phi here, right? Then we can build a theory. We can find the after the collisions and before collisions. We can apply momentum conservation law, and also we can apply energy conservation law. Energy conservation law and momentum conservation law, and we can build the equation for quantum wavelength shift. Right? Quantum wavelength shift. We can build the equation. I think we can prove this in the board. Page number 30 and 31 you can follow up. I will write two equations. What is the momentum conservation law and what is the energy equation? Energy conservation equations, right? The initially electrons at rest, the coming photon E naught and lambda naught. E naught and lambda naught. Right? And initial momentum is P naught. Then you can see after the collisions, this is the x-axis. This is the scattering photon. Scattered photon angle is theta. Angle is theta. We can take energy E dash, momentum P dash, frequency lambda dash, like this. Angle is theta. This is the scattering photon. And electrons can move angle phi and EK kinetic energy and PE momentum of electron, right? Then this is the elastic collisions. We can apply conservation of energy and also conservation of momentum to the two directions. So the first one, we can apply the momentum conservation law. Initially, no any momentum for the electrons. Then moving photon is here. Initial momentum is P naught. No any momentum for the electrons. And here we can divide into x-axis P dash cos theta plus other one is PE cos phi. This is the first equation. And also we can write momentum conservation law to the y directions. But no any momentum, initial momentum to the y direction. And here electrons has momentum in the y direction, P dash sine theta. And here PE sine phi but minus. This is equal initial momentum, it is equal 0. So we can rearrange this equation P dash sine theta equal PE sine phi. This is the equation number 2. Right? In the third equation, we can apply the conservation of energy to the collisions. Right? Then what happened here? P naught, E naught. E naught is the rest energy. E dash no any E naught is the low energy of the photon. Initial energy we can write E naught, but in the photon at electrons in rest, so it has only rest energy m naught c square. M naught c square. And this side we can write E dash of the photon energy. E dash is the photon energy because photon is the zero rest mass. Photon has zero rest mass. This is the energy, Hc over lambda, right? And E dash also Hc over lambda dash. These are photons. And electrons in at rest, so we can write rest energy. And here we can write then Ek is the kinetic energy, Ek plus MEC square. I think you remember last lecture I explained the energy of electrons and something, then Ek plus MEC squared in the energy of electrons. This is the equation number 3, right? Then page number 30 and 31 is explained here. I think you can follow equations. These are the equations. Then these are the calculation. Energy and momentum calculation. We can calculate the equations. E naught is equal P naught C and E dash equal P dash C. Then we can substitute all the things here. Right? Please follow the page number 31. You can explain. Then at the end of the equation, you can see some equation like this. One over P dash minus 1 over P naught. End of the calculation, we can see is equal 1 over M naught C into 1 minus cos theta. When we can substitute the relationship, P naught can write as E naught over C or H C over lambda naught. H nu naught over C. This is equal H over lambda naught. Right? Also P dash can write H over lambda dash. So you can substitute the equation here. H value. And we call quantum wave shift. As delta lambda can find lambda dash minus lambda naught. This is the quantum shift. Quantum shift, we call this as the quantum shift. In this equation, we can write quantum shifts using E naught over C, H over lambda naught and H over lambda dash. We can substitute the equation number here 1 minus QT, then equation become 1 over P dash, 1 over P dash, this cancel can uh, divide by H in this equation. We can write here, this is lambda dash minus here lambda naught is equal, H can come here, H over M naught C and 1 minus cos theta. This is the equation for quantum shift. Right? You should know how to prove this equation. You have to write conservation of momentum and conservation of energy. In the conservation of momentum, we can divide into two directions, and uh, energy can apply according to the relativistic energy. Then this quantum wavelength, we call this as the quantum wavelength. Right? Then you can find they are giving only cos theta, theta value, scattering angle, and asking what is the scattering shift, what is the quantum shift, can ask, right? But you should know how to prove the equation of the quantum effect. Then here we can convert this into the energy change. Sometimes question can ask what is the energy change of during the quantum effect, quantum shift. What is the energy change? Can ask, right? Energy change means E dash minus E naught. This is the energy change. We have to convert this. Energy change can write lambda dash minus E dash minus E. Then we can write E dash Hc over lambda dash minus Hc over lambda. And Hc can take out of the bracket 1 over lambda dash minus 1 over lambda. Then you can substitute this equation, delta E or energy change. Right? Then loss of energy. Question is asking what is the loss of energy. Then E dash minus E is the loss of energy, right? Sorry, E minus E dash, because the initially E value and now E dash value. E minus E dash, this is the energy loss of the during the quantum effects. Energy loss is equal delta E. Then question is asking what is the loss of energy. You have to find E minus E dash. It is can change Hc into 1 over lambda minus 1 over lambda dash. Right? E dash minus E can convert Hc over lambda dash, Hc over lambda. You can remember this, right? I will give one question. The equation also you should remember. Sometimes can give the find the loss of energy. What is this quantum shift of the of this process? Can ask, then you should know what is the quantum shift equation. I am not giving in the exam paper. I am not giving. This is the quantum shift equation. I am not giving, right? Then you should remember it. Okay. Question can ask one question. If the incident X-ray photons have a wavelength of 29 into 10 minus 12 meter, picometer something. No? What is the corresponding maximum change in energy. Maximum change in energy. U1. Maximum change in energy of the X-ray photons caused by the quantum scattering process. What is the corresponding maximum change? Now, you should remember the equations, right? Quantum scattering equation is lambda dash minus lambda is equal h over mec, mass of the electron and the velocity of light, 1 minus cos theta. This is the equation of the quantum shift equation. The question is asking what is the maximum change in energy of the X-ray, right? For the maximum range, maximum shift occur when what is the theta value when maximum changes occur? 1 minus cos theta. Then cos theta can change 0 to 0, 30, 60, 90, 45 like this. For the maximum energy, what happened for the theta? Cos theta. We can see maximum shift can occur when theta is equal 180 or 5 radi. 180. 180 means minus 1 because 180 is the minus 1, it's become 2. Right? Then lambda dash minus lambda t is equal h over mec into 1 minus cos theta. Cos 180 is minus 1. Then it becomes as minus minus plus 1, 2. 2h over mec. This is the maximum value. Then question is asking what is the maximum energy? Maximum energy is cos theta in this equation, right? So we can write maximum energy E dash minus E equal hc over lambda dash minus hc over lambda. G is me, right? Then we can take hc 1 lambda dash minus 1 over lambda. Right? In this equation, you can find when maximum shift occur, what is the lambda dash value? Then you can substitute with lambda dash to lambda, right? Lambda is given. Lambda dash can find here. For the maximum shift can occur when theta is 180. Then you can find lambda dash. You can substitute lambda dash here. Then you can find what is the maximum change in energy. This is the maximum change in energy, right? Then question will ask what is the loss of energy? Loss of energy, this is E minus E dash because then initial energy here, final energy here, then loss of energy. Okay? Right. I think you can understand the quantum shift, then you should know how to prove the quantum shift. not in BT1. Sometimes it can be come the final exam or thing, right? But then you have to know how to calculate the quantum shift and how to calculate the energy of the quantum shift, right? Equations. Then we have some theory parts. Radiations with matter. I think we have to cover only 4 sessions today. Next, we have to do the 5 to 9. Yes. 1 to 9 session, NBT2 will cover, right? You have 2 questions, essay question, but here some parts, consider some parts A, B, C, D like this. It's can related photoelectric effect, Planck constant, quantum effect, and other theories. Okay. So follow the all things I'm doing in class. It's very important. This is the quantum shift equation. I discuss it. Then you can see some theta equals 0 value. Then what happened? The intensity and lambda. You can see theta equal 45. Lambda not lambda. Theta equal 90. Two peaks can see. And theta equal 135. Two peaks can see in the graphs, right? This equation is quantum shift equation. Then photons and wave revise. Radiation with matter. What is the next one? De Broglie hypothesis. Next day we can conclude it. Session number 5. This is also can explain, but we will do next day, right? And Heisenberg uncertainty principle also related to the next day. In session number 4, no PowerPoint. Interaction of radiation with matter. Interaction of radiation with matter. This is related to the hydrogen spectra. It is hydrogen spectra, no, spectrum. Some absorption spectrum and emission spectrum. Then it can get the more idea in the next part. Hydrogen spectrum or something, you can get the more idea about the radiation with matter. Right? Then these are some informations for the ultraviolet light. We think photons of energy between some 5.2 to 7.8 in atmosphere. No any PowerPoint or something. And oxygen atom can absorb such a photon and get this associated into two oxygen atoms, right? And also can combine with the oxygen molecule and form the ozone. This ozone molecule absorbs an ultraviolet light photon of energy between 3.4 and 5.2. This is the one thing for the example, for the interaction of matter, right? And in the atomic photoelectric, then we call this as the photoionization and atomic photoelectric effect. Then as the result of this photoionization, a beam of ultraviolet, X-ray or gamma passes through the matter, it produces ions along its paths. It's the amount of energy required to release the electron from an atom or molecule we call as the ionization potential. Then we can require to release an electron from one atom or molecule we call the ionization potentials, right? Then we can write the kinetic energy. This is in K is equal h mu minus I dash. Then you can read the course material in page number 37. This is more explanation can get the hydrogen atom, right? In the photoionization, we call this as the ionization energy. If we are taking the hydrogen atom, we want to remove one electron from an atom. we call the ejection of the electrons from the ground state, we call the ground ionization energy of the hydrogen atom at that H nu minimum is equal to 13.6 electron volt. And this is called as the ionization energy of the hydrogen atom. Or first excited, then after absorb this energy from or after releasing this energy can go to the excited state of the hydrogen atom. First excited, we call this as the ionization energy. In the hydrogen atom lesson, we can calculate this value, right? Then you should know what is the interaction of matter with matter. Then H nu, and also we call 13.6 as the binding energy of the hydrogen atom. So we have to escape the electron from the atom. We should provide the energy equal to the binding energy. 13.6 value we have to provide, right? I dash is called also as the ionization energy or binding energy. Okay. So you can follow this one. Beam of electromagnetic radiation passes through the matter. So intensity can change. This is the one matter. The beam of electromagnetic radiation passing this matter, then what happened? The intensity of the beam is reduced to the removal of scattering of photon along its path by some combination of photoelectric effect, quantum effect that can happen inside the matter. Right? Then beam of radiation is coming, then inside matter can happen photoelectric effect or quantum scattering, and also some productions can happen. So this, due to these interactions, what happened? The intensity can be reduced for the initial one. Initial one is E naught, and after the final one is E dash or I. I naught is the initial intensity, and the final one is I. Then what happened? Due to the interaction of this photoelectric effect can happen, quantum effect can have the reduce the intensity of the wavelength, right? And if the length of the passing length is x, we can write equation like this: I equal I naught e to the power minus mu x. X is the length of this matter. I is the now reduced intensity, and initial intensity is I naught is equal minus mu x. We call mu as linear absorption coefficients. Linear absorption coefficient is mu, right? For the given photon energy, right? Mu values is depend on the, mu is the constant. It depends on the absorbing material. It is depend on the material, right? For the given m value, mu value, energy of the radiation, different interaction, periodic different energy. I naught is equal minus mu x is the length. So intensity can reduce the previous value, right? Then you can follow the page number 30 and 30 and read and get the idea. This is important for the nuclear and particle physics session, because one prerequisite of the modern physics is for the particle physics, right? And also, then we know then some atoms, according to the Planck's law and something, we know the some can goes to the higher state by absorbing some range of radiations. Some range of frequency can absorption spectrum can see the absorption electrons, and also we can see consist of the some frequencies emission spectrum of the atom, right? Some are absorbing and going to the higher excited state, then corresponding spectrum we called as the absorption spectrum, and also some atoms goes to the highest level can goes to the lower state by emission of the electromagnetic radiation. It is correspond to the emission spectrum, right? And also then energy difference. In the higher levels, we can discuss in the Planck constant and E1, E2 like this. Energy difference, E2 minus E1 also corresponding HF. HF. This is the Planck constant, Planck's theory. It is also related to the Bohr theory. For the hydrogen atom, we can find E minus E1 as the H nu. We call this as the formula. In the hydrogen atom, you can study about the Bohr formula and things, right? So, read this session. It is useful for the hydrogen atom. Then Frank-Hertz experiment is the one experiment. I'm not going to touch this because it's complicated one, right? So you know, just for your information, you can read, but it's complicated for the Frank-Hertz experiment for you. This is useful for the special degree student. Then you, if you are willing to do the special degree or something or higher study, you can read this and can get more idea, right? And read this one, but radiation with matter, this is useful for the next sessions. And also, I equal I naught, this equation for the nuclear and particle physics, you can see, right? I think de Broglie hypothesis and matter waves, we can discuss next day. 4, 5, 6, 7, 8, and 9. Schrodinger equation, we can start. The next time independent Schrodinger equation. Up to session 9, can go for the NBT 2, right? I think next day is school